Okay. Thank you, and welcome back to topic 5, digital representations of unit. Today, we will have 3 speakers in this particular topic. The first talk will be on an approach to interoperability of units of measure by Bob Hanisch and also Stuart Chalk. Bob Hanisch is the director of the Office of Data and Informatics, Materials Measurement Laboratory at the US National Institute of Standards and Technology, or NIST. His teams provide data management and data sharing solution for the organization and manages the portfolio of standard reference data. He is a member of the Research Data Alliance and chairs the Core Data Task Group on digital representation of units of measure. He earned his PhD from the University of Maryland, studying extended radio emission in clusters of galaxy, and also Professor Stuart Chalk is a professor at the Department of Chemistry at the University of North Florida. Although he's trained as an analytical chemist, Stuart's interests are now in the area of chemical informatics and data science. Stuart's research is focused on machine readability of physical property data, chemical terminology via the IUPAC Go book, automation, extraction, and annotation of chemical property from PDF files, and scientific data model. The second talk is on the recent development of QUDT, quantities, units, dimension, and type, and that will be delivered by Dr. Stephen Ray. Dr. Stephen Ray is an independent expert in the use of ontologies and formal representation to ensure unambiguous definition of terms and relation, particularly the interoperability standards in smart grid, the Internet of Things, manufacturing, and also medical devices. He has a 27 years of track record of initiating and leading technical R&D projects related to information standards at the National Institute of Standards and Technology in the US. And that was followed by a decade as a distinguished research fellow at the Carnegie Mellon University. He's currently the CEO of QUDT.org, a non-profit to provide semantic specifications of units of measure. And our third and last talk is on the units, scales, constant, physical quantities, and dimensions in Wolfram language. And this will be delivered by Dr. Michael Trott. Dr. Michael Trott studied physics in the Humboldt University in Berlin, and he received his PhD in theoretical solid-state physics at the Technical University of Ilmenau. He has been a member of the Wolfram research since 1994, and in 1996 he wrote the first line of code for Wolfram Alpha, and has since worked there till now. Today he's the chief scientist of Wolfram Alpha. He helps helping in realizing the dream of making the world's knowledge of quantitative sciences easily accessible, especially physics, chemistry, and biology, and also putting mathematics in a form that both computers and human can understand and use and extend. Outside of this, Michael's interest is in the early history of the metric system and the Vienna circle. So without further ado, we will have the first speaker. Thank you.
Hello, I'm Robert Hanisch from the U.S. National Institute of Standards and Technology. And I'm here today with my colleague Stuart Chalk from the University of North Florida to talk about an approach to interoperability for units of measure. Units are ubiquitous and fundamental to all practices in science. Units have, until now, or until recently, really been for humans. We read about units in publications, and we see symbols and so forth, and everybody basically thinks that there is no problem, that we have solved the ways to represent units of measure. But in fact, when you're talking about computers and making units understandable semantically by computers, units are not solved. We need definite identification of units of measure for machines in order to facilitate interoperability of data. If you don't know the units and you can't properly compare them, then you really can't do metrology or other sciences properly. There are a number of drivers for improving interoperability of units of measure. For example, the United Nations Sustainable Development Goals require integration of data from very disparate resources, and those resources may have units represented in very different and incompatible ways. CODATA is initiating a decadal program, which is also emphasizing cross-domain grand challenges, where interoperability of units of measure will be essential. And this is a tenet that underlies the FAIR principles, findable, accessible, interoperable, and reusable data, where metadata needs to be sufficiently detailed such that units of measure are understandable by machines. The good news is that there are a number of well-established digital unit representations. We don't need another standard, but we do need to facilitate interoperability, and we need tools that can convert and find units and metadata describing rich data sets. There are several activities around this problem of representation of units of measure. There's a CODATA task group on the digital representation of units of measure, DRUM, of which I am the chair, and Stuart is a colleague of mine working on that task group. There's also CODATA engaging with the international scientific unions and the DRUM in order to solicit use cases and challenges. And in the social sciences, there's the Data Documentation Initiative Cross-Domain Integration Program that is also being done in collaboration with CODATA and the DRUM task group. The Research Data Alliance also has an interest group that is focusing on the UN Sustainable Development Goals. And so there are many groups now engaged in trying to rectify some of these challenges. I'll now ask Stuart to take over and talk about the current landscape for representing units of measure.
Thanks, Bob. The current digital unit representation landscape is quite varied, and as you can see here, there are a number of different specifications and/or implementations, kind of separated out into both encodings and ontologies. Now, these are just examples of these two categories, but what has happened is individual disciplines have basically decided they needed to formalize units within that discipline, and therefore they have created their own encodings. As far as ontologies are concerned, there are a number of ontologies around units, QUDT being probably the biggest one right now, and the presentation that comes next is going to go into QUDT in a little more detail. Now, in addition to these specifications and implementations, which are text-based and often used in databases, units are also represented within software and operating systems across different scripting languages, and also in document formatting standards. And so in terms of the different string representations of units, there are a number of variants. Next. You can see on this slide that I have aggregated a number of string representations of the unit, the mole, and kind of given you kind of like a picture of the variability that exists currently. clearly, it's important that these representations are used and understood, but the interoperability between these representations is very important, obviously, for making data interoperable in the grand sense. And so trying to develop a service to be able to identify and align these different encodings of units is an important priority. Next. In addition, there are just formatting strings that are variable for representing different units. This is meters cubed. And as you can see, there are a variety of different strings that represent that particular unit. And it would also be good if these text-based strings are able to be translated between the string representation and the appropriate unit that they represent. So we have to include those in any system that is developed. Next. Just quickly, a couple of very simple pain point examples. Here we have a slide showing data from different microscopy experiments, where, as you can see, not only are the units of measure not represented, not labeled in the present in the pictures, but also the number of digits used to represent the numeric value is certainly far beyond the number of significant digits. So clearly we need to make sure that the community does at least annotate units of measure wherever necessary. Next. In addition, this is an example of the representation of molar volume, the unit centimeter cubed per mole, in a PDF document, where, as you can see, there are a number of different representations. Some are good, some are at least the appropriate unit, but are not particularly well formatted, and some are actually clearly wrong. And so in terms of natural language processing applications for units, it's important that that publishers, in addition to authors of papers, make sure that unit representations are in some fashion standardized so that they can be made interoperable. Next. So there is a lot to understand about the extent of the digital unit representation landscape in the different ways in which units are implemented. We need to gather use cases to understand the scope of needs to support interoperability of these different unit representations. We also need to capture a significant number of pain points to identify additional solutions that are needed to solve those pain points. As part of ongoing efforts, we need to determine what tools and services, therefore, we need to support any and all entities that need to identify and align units of measure so that they can be made interoperable. And we want to reach out to different communities and disciplines to make sure we understand their needs, so they understand their needs and approaches to using digital units moving forward. Next. Thank you very much for your attention, and we're happy to answer questions in the discussion.
Thank you.
Hello, and thank you for the opportunity to present an update on the QEDT ontology at this Congress. My name is Steve Ray, and I'm the CEO of QEDT.org, which is a 501c3 public charity nonprofit incorporated here in the United States. So I'd like to start by just giving you a listing of some of the key features of the QEDT ontology. It is a set of modular graphs distributed both as OWL and shackle, the shapes constraint language, accompanied with a set of vocabularies of units, quantity kinds, dimension vectors, physical constants, systems of units, and systems of quantity kinds. For the linked data community, these are all fully resolvable URIs, all the vocabulary instances and quantity kinds, all the individuals, as well as the URIs for the graphs themselves. One thing that's somewhat unique about the QEDT ontology is we have a well-defined grammar for naming the unit URIs, which makes it somewhat easier, more predictable how to find a given unit of interest for inclusion in your own application. All of these files are encoded as Turtle RDF. And in addition to both the files, a set of static web pages to explore QEDT, we also offer a dynamic Edge browser. Edge is a product from Top Quadrant, which offers a dynamic viewing experience as well as Sparkle querying and a Sparkle endpoint. So finally, QEDT is licensed under a Creative Commons Attribution 4.0 license, which means it can be embedded inside commercial tools for sale without any need for any royalties of any kind. And I refer you to the QEDT.org website for specifics. So here's the essence of the ontology itself. We have the notion of a quantity, which is a contextual concept. Say the height of a building would be a quantity, which has associated with it then a numerical value, say 15.2, a unit, say meters, a quantity kind, which is in this case length, as well as a dimension, which points back to the dimension vectors inherent in any system of units and quantity kinds, such as SI, where you have, of course, the 7 base dimensions, as well as 7 base units. So that's the essential pattern. Here's an example of a very simple use of QEDT, which is just a single quantity which has a numerical value, 72 you see in the example, an associated unit, and the unit is then in turn associated with a quantity kind. This is the very simplest way. You can see some code there, how it would be written. There are more complex patterns. For example, if you wanted to store multiple pairs of values and different units, you can also do that in the QEDT ontology. So everything, as I mentioned, is defined in terms of these dimension vectors. And the reason that's so important is it then allows automated unit conversion, dimensional analysis, these kinds of things, commensurate units that can be checked either in Sparkle itself or Shackle or your own application, of course. Here are some statistics for the current population of units and quantity all available for distribution. I'd like to also mention that QEDT does contain cross-references to many other international standards so that you could, for example, use the UCUM literal representation for a unit to find the QEDT equivalent, and from there navigate to the quantity kind and do any computations you might care to do. So we are trying to have many such connections there. Here's a partial view of the web browser interface. You can see human readability. We have LaTeX descriptions for many of our units and quantity kinds. We cross-reference the symbols, and you can see on the right there the other standards that have an equivalent to a particular unit. I'd like to spend a few minutes discussing this issue here, which is that QEDT has served multiple distinct communities. And I think this is important for anyone trying to standardize on how to represent units. Initially, and probably earliest, was the linked data community, which is more interested in up-to-date, the latest version of something, but fully resolvable URIs. So they can simply make reference to a URI and they receive back a snippet of code which describes what that unit or quantity kind is all about. Now that's quite different from the industrial use community, who are more interested in careful management of version control. They want to download these graphs and have them remain fixed in their own application until such time as they are ready to make a careful migration to a newer version. And we use a GitHub release mechanism for this, such that you can use it as a downloaded artifact rather than online through the linked data paradigm. We offer both the choice of the OWL representation of the schemas or Shackle, a shapes constraint language. OWL has been around, of course, much longer. The shackle representation allows a more expressive capture of some constraints in behavior, which we take advantage of, for example, in that Edge browser for dynamically inferring properties, which might otherwise have been explicitly stated in the vocabularies for the linked data community. So we want to make sure it's available for use with or without the need of using a reasoner in conjunction with it. So you can take your pick in that sense. But this is important to think about in terms of what should be standardized. Do you want to have a core from which one can infer other properties, or do you want to go ahead and explicitly assert all of these other inferences for simple downloading? It's not an easy question to answer. Finally, here are some links to the Qedt homepage, and it has actually cross-references to our GitHub repository, documentation, many other resources. So in the interest of time, I'm not going to go into all the other things you can do with Qedt, but I would like to stress that we are an open source project. We depend upon community involvement for contributions, error checking, new units, domain expertise, and all. And I would invite you to consider participating in that way. So with that, I will stop and will be available for any questions you might have. Thank you.
Good afternoon, everybody. Thank you for coming to my talk. I want to talk about units, quantities, physical quantities, and physical constants in the Wolfram language today. First question, why do we care about units in the technical computing systems? And the answer is pretty simple, because many real-life computations that modeling the real world do contain dimensional parameters. This means one needs a semantic computational encoding of observables and results of observations, meaning measurement results. That's why in 2012, in the version 9 of the Wolfram language, we introduced the function quantity with arguments magnitude and unit and a bunch of related functions that work with it. We had already started a couple of years earlier working with unit when we worked on Wolfram Alpha. That was released in 2009 and now powers personal assistants like Siri and Alexa. The reason is that a good fraction of quantitative queries that people ask are either direct unit conversions or queries that need units to even formulate a question, or an even larger number of queries that have a quantitative result that turns out to be a quantity with dimensional answer. So before going into the actual quantity framework, I want to quickly discuss the syntax of the Wolfram language so that some of the examples become easier to understand. We only discuss the interactive in-out paradigm, not the remote computation of a batch session. So here we have an input, and we can evaluate it, and we see here in and out. We will frequently see in-out with a little bit grayed out with a bullet, like this one. And the reason is this is from the last time I had this mathematical notebook open, and if I evaluate it, then it will instantiate it to the current in-out in this session. I will not evaluate everything for timing reasons. Wolfram language functions are typically uppercase and internally capitalized. So contour plot, quantity magnitude. Square brackets are used for function application, like sinus, log base b, comma x. Curly braces are used for ranges, domains, iterators. And the percent sign refers to the last result. So for instance, if we evaluate this input, we can refer to it and numericalize it with any precision. The arbitrary precision arithmetic becomes very handy when we deal with quantities, because quantities frequently are only measured to a finite precision. Now with respect to the computational representation of things, other than mathematical objects, one needs dates, molecules, quantities, an object of the real world to really compute with them. So here's a quantity 3 meter. I can compute this. The result is nicely formatted, easy to read, has a tooltip. I can take the result, add something, I can convert it to another unit. Here's the current time instance, and I can say what is now minus this, and it shows that the difference between two time instances is, of course, a time difference. And then we have this concept of entities in the Wolfram language. Entities are all kinds of things of the real world, like persons, elements, music recording, dog breeds, food, and so on. Here's, for instance, the entity New York City. I evaluate it and it becomes this yellow box. And I can ask questions about this, like how many people live there. And we see it's a quantity with the unit people. Now a quick overview over the main quantity-related functions. So we have already seen there's quantity and a bunch of other built-in functions to represent and work with quantities, physical quantities, and physical constants. They all have a compact and editable output formatting, which is very convenient, easy to read. They work smoothly together with visualization function, numeric and symbolic computation functions. And units, meaning the second argument of quantity, can be classical units like meters, seconds, but they can also be physical constants like the speed of light. And the default output, metric or imperial, is customary, depends on your GeoIP. That's a quick overview. So in the center of it are quantities like 3 centimeters, 5 meters. They have units inside. Then units have physical dimensions like length, mass. Then there are quantity variables. They can be potentially be named like voltage V. Then we need, of course, uncertainty computations if we work with units. And we need physical constants that define units. And then many things like geo, dates and times. So here's a list of the most important functions. Quantity we have already seen. Quantity variable is something like the quantity variable V representing an electric potential. Unit convert, unit simplify, also pretty self-explanatory. Unit dimensions, mass, length, time, temperature. And there are around 2,000 other functions. The Wolfram language has currently around 6,000 symbols, and this is a lot, but you don't need all of them all the time. But adding a couple thousand more units to remember would make it not easier. That's why we have a very convenient way to type them in. For instance, you have a quantity, and then it already proposes the most commonly typed units at this point. There are still at this level many to choose from. Or you can use control equal, which allows any natural language input. That's the functionality we use on Wolfram Alpha to understand natural language. For instance, here the product of Boltzmann constant times 300 degrees Kelvin. The result is fully computational, so you can convert it, say, to electron volts. If you have a large number of such natural language expression, you can use the function interpreter to process them programmatically. For instance, here's 2 times 198 kilometers, and so on and so on. And this gives a euro amount by the end of the day. Couple words about the scope and breadth of the data about units and related functionality that we have. We have around 5,400 different units, obviously all SI units, including prefixes, but we have also many thousands of historic and international units. Here are some examples, like here are some GGS units, genetics, some from astronomy, some historical ones. And we have also collected more than 12,000 compound units. Of course, you can form any compound units that you ever wanted, but this doesn't mean people use it in practice in a certain field. Knowing what kind of compound units actually occur is very important for making appropriate choices for simplifying compound units. Physical quantities, we have around 2,700 of them. They work very similar, also have a tooltip. And here's a list of them with their standard name, their canonical units, and their dimensions. Physical constants, we have around 320 of them. Obviously, all co-data ones, the latest and the historical co-data values. We supplemented this with constants from astronomy, cosmology, particle physics, speed of light, Planck constant, Avogadro constant, Boltzmann constant. We also have ones that are related, say, to Earth flattenings, ratios of mass-sun. And you see, whenever possible, we have exact values of them, which is not possible with the new SI. Otherwise, we very carefully keep track of what's the current precision that the latest co-data values allow. So I want to show some quick examples. Here's a sum of 3 lengths, 12.7 meters, 3.603 kilometers, and a small factor multiplied by 5 light years. We can evaluate it. We can convert it, say, to miles. Here's a ratio of 3 joules divided by watts. Note that we don't simplify automatically the units, but we keep it as joules over watts. But of course, you can simplify. And here's a mixed radix quantity, which very nicely formats. Mixed radix obviously important for feet, inches, hours, minutes, seconds, and so on. Some example for physical constant. Here's a Planck constant. I evaluated, converted to SI base, which is an exact number, an exact fraction. Here is the Josephson constant, also exact. I can, of course, numericalize it to any precision. And here's the famous Eddington-Weinberg relation. I can just evaluate it. It stays symbolic. I can convert it, and to the relatively low precision, we know the Hubble constant. These two numbers indeed agree, and future physics will probably show the deeper meaning of this relation. Now, physical constant. Here's a quantity variable for an electric potential called V. Here are its dimensions. current, length, mass, and time. Not unexpected, the canonical unit is volts. Here's the Lagrangian of a classical pendulum. Note that these are not just symbols, they are all physical quantities. This means we know the dimension of this object. And we can get, say, the Lagrange equations and then make a small angle approximation to get a classical formula for a pendulum that we learn in school. Some small applications, how to work with units. We have 1200 plus formulas from physics. Here's, for instance, the Planck radiation law with the wavelength as the independent variable, and the dependent one is spectral radiance. We can compute explicit values by using concrete wavelengths and temperatures. Here's a nice example, shows nicely how everything works together. Take F equal ma and have a given force, a given mass, and that's the acceleration expressed as second derivative of time. But note that it's not just a symbol, it's actually quantity variables. This means we can supplement this one with initial conditions, then solve. Now we have the solution of differential equation, and we can plug in a time to get an explicit result for the position. Okay, some data applications. Assume you want to do some more complicated searches. For instance, you want all elements with a density between 9.1 and 10.1 gram per cubic centimeter. So just to formulate a question, you need obviously units. And we look at all elements, we get all metals with this density, and bismuth probably be the most known one among exotic metals. We can look, for instance, what are the carbon spectral lines that are in the visible range. We can visualize this. A thermodynamic computation, what is the viscosity of air at a certain pressure and temperature, what's the current Sidereal time in Paris, and the result is a mixed radix quantity in hours of right ascension, minutes, and seconds. Some applications for units and quantities in daily life calculations. These are entities of type cookie that have chocolate chips added. We have around 100 different of them. What kind of nutritional values? Or given a 14-year-old male, what's its height within 1 sigma? Human growth data provides us with this. Socioeconomic data are a very interesting case because they have some units that are typically slightly outside of the SI, like persons or counting units. So here, beer per capita production over the last 50 years, we get back a time series. And the elements of the time series themselves are quantities of dimension kilogram per person and year. Some applications from geography. Here are some aerial images of the northernmost and southernmost points of the Machine, the Lumber expedition. We can calculate, say, the distance between these 2 points to millimeter precision. Here are the geogravity data, and we see a relatively large horizontal component, which is conjectured to be one of the reasons why our meter is 0.4 millimeters off. Computational chemistry and genomics. Here's a coffee molecule. We can represent it as a symbolic object, and as such, it has, of course, properties. For instance, we can calculate its molar mass, its energy, and the force field minimization, and we can calculate its principal moments of inertia. Here, let's retrieve the mean male height and male weight for 375 dog breeds, pretty big dogs and pretty small dogs. And we see in a log-log plot, they lie pretty much on a line. And we know from general allometric scaling ideas that we would have a relation that the weight is proportional to height to the alpha with an exponent between 2 and 3. And we can quickly carry out the optimal fit to this nonlinear model, not just of the log, but the original one, and get 2.4 as the exponential scaling parameter for dogs. Let's look at a slightly more esoteric example. Pokemons. We know that humans' weight is log normal distributed. Human height is normal distributed. What about Pokemon weights? There was a paper in Journal of Physical Society 2019 investigated. If we make a plot on a logarithmic axis, we see in a first approximation a Gaussian curve. So Pokemons are indeed having a log normal weight distribution, and we can say compute the optimal distribution for the parameters of the log normal distribution. And if we look at them, they really span an enormous amount of scales from 90 grams to nearly a ton. So, a couple of words on extension and some potential issues. Let's take 22 euros per hour. We can convert this, for instance, in dollars per minute, where we have to do actually 2 conversions, the simple ones being hours to minute, the more complicated one, the one being euros and US dollars, where we use the current exchange rate. But what about euro from 2006? To indicate that this is an old euro, we have the concept of a dated unit, where we can say from when it is, and then we convert, say, a euro from 2006 to a euro to 2016, and we see around a 15% change due to inflation. Dimension of angles. Everybody who follows metrology knows that there's a discussion about the topic. Do angles have dimensions, and is it better to have them, or is it better not to have them? In our system, we decided to consider them to be having dimensions. This means something like an angular velocity has dimensions angle over time. Counting units is another interesting subject that you need for practical applications, even if the SI is not very specific what we should do with them. Like you have 5 slices of bacon, 8 cloves of garlic, 200,000 web hits. To deal with them in an optimal manner, we have many of them as built-in ones, and obviously there are always more things you can count than one can have. Nearly every countable down is something you could count. We also have the possibility for users to extend the system with more counting units. Non-multiplicative units, meaning additive and logarithmic ones. There is some ambiguity, for instance, in the degree Celsius. SB 811 from NIST says that the degree Celsius can be considered either as a difference or as a scale. Here we have the degree Celsius, and here we have degree Celsius difference. So we carefully differentiate the two, because if you convert them to kelvins, one of them is more or less, of course, the same, where the other one is, of course, a much bigger number. Earthquakes are complicated because they are logarithmic. They are complicated for the system as well as for users. Not only being logarithmic, they are having some other complications due to slightly fuzzy conversions. Some representation details. Normally in a symbolic system, if you have x over x, you are related to 1. But what about 2.8 micrometers by meters? Do we want to convert this to 2.8 times 10 to the minus 6 as a unitless quantity? And we decided not to do this by default, because 2.8 micrometers over meters is really something else than 2.8 microseconds over seconds. If you wanted, you can force the system to make them dimensionless. Just a couple of words about physical constants. Here are some random ones. And we have one very nice property, equivalent forms, which gives you various versions to write a certain physical constant, in this case the Bohr radius. It is nice because once you have a sufficient amount of these equations, you can actually do algebraic computations with them. For instance, figuring out what's the influence of an error in one of the physical constants. Here we take this list of representations and plug in the latest code data value, and it matters which order you do all of this, because the resulting precision is slightly different. Some application of working with dimensions. Dimension analysis still very popular and in use. Here's a very classic example, Taylor's estimation of the explosion power of the Trinity bomb. So what you have at your disposal, you have the mass density of air, you have the radius of the ball visible, and you have the time after which it was photographed. And this uniquely gives you this quantity that you can form of dimension energy. You can plug in the values, and you get around 26 kilotons, which is pretty much the right result. Another application of the use of dimensions is the de-dimensionalization of equations. For instance, you have a time-independent harmonic oscillator Schrödinger equation, and you want to get a form that is free of any units and dimensions. So we have this function non-dimensionalization transform with old variables, new variables. Here's the result. And we also get the explicit instructions what to do with the dependent and independent variables and the parameter to get to a pure equation with no dimensions. Okay, as said, measurement results always have uncertainty, so it's important to do computations properly by taking uncertainty into account. Here's a very simple example. Take one with pure numbers, no units and quantities involved. Of course, we could do it with units and quantities. Say we have 2.4 plus minus 0.1. The function in Wolfram language to represent uncertainty is around. So we have this, and then we can carry out proper Gum-style arithmetic that takes all correlations, potentially vector valued, into account with correlation matrices, and we get this result. Of course, you could also just substitute it, but then because we missed any correlation, we get a much larger uncertainty. Being able to do it properly with uncertainty is, of course, important for more and more domains, like the Kepler mission that looks for the exoplanets. They report very nice error bounds and everything, so we can take them and visualize them and see where a potential future habitat for humans might be. Sometimes one doesn't just want to do an uncertainty calculation, but one has to be a little bit more precise because one needs very high moments or the active distribution. We can work with built-in distributions. Here's a so-called quantity distribution, where we have voltages that are distributed according to a Wigner semicircle, a uniform distribution for the current, and then we can use just Ohm's law to calculate what is the expected value of the resistance, and we can also calculate the actual distribution. And here are some visualizations. So the half circle for the voltage, the uniform for the current, and the resistance is more complicated. Here's a closed form for the distribution. Okay, and I think it brings me nearly to the end of my talk. So quick summary. There is a very detailed documentation of all of the 2000 unit and quantity related functions that we have in the Wolfram language. If you go to the Wolfram language documentation, here's a snapshot of the website. Then for some more advanced application examples for the version 12 of the Wolfram language that came out 2 years ago, we prepared a larger number of examples, what you can do with all the functionality available. And last, I put a version of this talk with some more examples in the cloud. You can just go to this address and try all these examples yourself, can modify them, rerun them, and you don't need an account to do this. And if you have any questions for me or the units team at Wolfram, don't hesitate to email me, and I will answer as fast as I can. Thank you very much for your attention.
Okay, thank you. Thank you very much for the 3 very interesting talks on the digital representation of the units, and also some examples of where they are used. For example, in symbolic manipulation in the last talk by Dr. Michael Trott. And then, of course, there's also the example of QUDT and where, you know, we have the units that are represented in unit representation that is used by many of the people in the industry for different purposes. But I think from the presentation in this session and also from the last session, we begin to see that a lot of the units are now actually used by machines, and in addition to human beings. And there's also the issues of machine-to-machine communications. So the definitive, unambiguous definitions of the unit is important. And Stuart touched on the point of currently we have a lot of, maybe quite a number of digital representation of the unit, but perhaps the encoding systems are slightly different from each of them, and how do you then enable machines to interoperate between these different form of encoding, right? So today we are very pleased to have 2 of the 3 speakers here in our panel of discussion. So first we have Bob Hanisch. So I will have Bob Hanisch introduce himself.
Yes, hi, I'm Bob Hanisch. I'm at the National Institute of Standards and Technology, and I have several hats to wear, including being a member of the expert group of the CIPM task group on digital SI, and also the CODATA task group, chair of the CODATA task group on digital representation of units of measure. And let me just say, I find the presentation from our colleague at Wolfram to be pretty overwhelming. They seem to have things well in their grasp. On the other hand, I also find the presentation from my colleague Steve Ray about QUDT to be incredibly important, because here we have a lingua franca for units that I think is incredibly important for interoperability, and links back to previous talks in this workshop about FAIR and interoperability. I appreciate what Wolfram is doing, but it seems to me they're doing it in their, in their closed ecosystem. And I wonder, Steve, if you have a comment about that as well.
Yes, actually, I was going to mention that. So let's see, I'll take Thomas's invitation. So very briefly, my background is in interoperability and standards for my entire career, which included a large chunk of time at NIST myself. So I think that in the context of this workshop, or this Congress, the FAIR principles and the notion of interoperability as essentially a light touch between applications, I think is one that I have long subscribed to. In other words, you're right in the sense that if everyone used Wolfram, then right, we would have interoperability because we're all using the same tool. But of course, the real world doesn't work that way. People have all kinds of reasons, and they have their own contexts. So I've often thought of interoperability as a essentially loosely connected application. So you want to be as gentle as possible in terms of tying systems together. You cannot assume they're going to behave a certain way, various systems. And that's where I do believe that, data models or ontologies, which focus on the definitions of the terms, but not exactly how you're going to use them or what application you're going to put them to, is the sweet spot for interoperability and fair data. So I'm a big proponent of source and universal availability of these kinds of concepts. And that's kind of represented in our philosophy of how we're putting QUDT forward.
Yeah, it seems like we have a problem of the Tower of Babel, right? There are so many languages. Hopefully, at least there will be a few dominant languages that we can all use to communicate across different boundaries and systems. So I suppose in the digital world, we have a similar situation. Yeah. Okay.
I'd like to say one quick comment on that, which is that we're never going to have a single language, of course, but a colleague of mine in University of Toronto, Michael Gruninger, has always talked about a notion of semantic transparency, which means you can use whatever terms you like as long as you're very clear what you mean by those terms. And that way you can allow community localized domain languages as long as they define what their terms mean in an unambiguous way.
Right.
Yeah, that's indeed. So like today, we now start to have natural language translation, and you can understand each other without knowing the language, right? So, okay, I'll have Victoria post some of the questions that our participants have posted on the chat board.
Thanks, Tom. And there's a question that kind of touches on this subject from Marcus Foster, which he directs to, I guess, Stuart and Bob, but I think Steve can also answer it. And he asks, of course, many quantities share the same units. So to promote quantity correctness, the quantity kind should also be specified in digital systems. This is recognized in QUDT, but rarely in programming languages or computational software. And do you have a comment on that?
Well, I wish Stuart were here because he's more the domain expert than I am. I am more the proponent of finding solutions to this. Steve, help me out here.
Well, that's correct. I mean, I think the notion of a quantity kind is often neglected in people's thoughts. They think that they've said everything they need to say when they describe the unit. But in fact, the quantity kind, which is what is this thing that the unit is measuring, whether it be length or something. And in QEDT, actually, we have a whole hierarchy of, if you like, increasingly contextual quantity kinds. So there's length, but there's, for example, height or width or depth. Okay, those are more specialized versions of length in the context of gravity, right? And it's what's up, what's down. So we use the SCOS simple knowledge object system approach for relating more broad or narrow concepts in our hierarchy of quantity kinds to further describe the context, if you like, of the unit being used.
Thank you.
Mm-hmm.
And another question from Blair Hall at MSL to you, Steve. And he says, I saw that QUDT uses an internal representation in which you can express not just dimensions, but ratios of dimension vectors. Can you say a little bit about the decision to use ratios?
Yes, absolutely. In fact, this is even touched upon by our Wolfram speaker in terms of meters over meters or degrees over degrees. Just because a unit is dimensionless does not mean it's commensurate with another dimensionless unit. So it's important to keep the, if you like, the canceled out units in the encodings or in the model itself. In fact, I would argue ratios are the easier ones to do, which we have done for many of our quantity kinds. But there are more complex dimensionless quantities, which are not simple ratios of the same quantity kind on numerator and denominator. We plan to go there and actually have a more rich representation of the, if you like, what's under the hood behind a particular dimensionality. But we haven't tackled that one yet. It can get arbitrarily complex, of course. With think of any equation you like, any dimensionless equation, it can have all kinds of properties that cancel out on the other side. So that's a challenge we have going forward. We've done the easy one, which is simple ratios, which does cover, I'd say, the 80-20 rule, 80% of the cases of simple ratios of things. But it keeps you honest. Mix up a temperature ratio with a length ratio and expect to get anything sensible out of it.
I would just add that this is a topic that totally invigorates conversation amongst the most obsessive people that I work with in the metrology community. They get very upset about these quantities of dimension unity or dimension zero, and boy,
Yeah.
it leads to incredibly intense conversations.
Thank you.
Another question from Jan Herman at NMIA. Are we at risk of replacing the problem of non-uniform representation of quantities and units with the problem of non-uniform implementation of a uniform representation?
Wow. That's a heavy question. I don't think I can do justice to that question off the top of my head right now, actually. Bob, do you have any thoughts on that one?
Yeah, sure. We're at risk. Wow. Yeah, that's a enigma in the question itself. This is a complicated problem. We need to find some sort of lingua franca, be it the equivalent of Esperanto or something that allows us to unambiguously represent and convert units of measure. It's I don't know, maybe it's not that complicated a problem, except that we have to recognize that there are communities of practice, and we have to recognize that we can't impose upon them something from the top down. We have to embrace what exists and come up with a level of interoperability and communication that works. Would you agree, Steve, with that? I mean,
yeah, certainly that, yes. I mean, there are still many very, very tough problems to go. The other one that didn't come up, which is what I thought was where Jan was going, which I don't think he was, but is nonlinear units and nonlinear scales.
Yeah.
That again, it becomes very complex. I was pondering scale the other day, and of course, there are in earthquake fields, which is not my field, issues about ground movement and distance from an epicenter. I mean, these are not straightforward conversions if they can be converted at all. Gross tonnage for ships is a unit used in taxation, which is not linear and not directly convertible to other things. So there's all kinds of units that people use which are not well behaved in the sense of linear. They might not have a zero offset, you know, certainly our temperatures don't. So there's plenty of really tough problems to go. So the easy ones can be done, and that's most things, but there are certainly communities that have some very, very difficult issues that they face.
Yeah.
Okay, there's a question that also then kind of draws on this, and that is from Jarir at NIMT. What's the organizational body who's responsible for overarching coordination or for linking all these codes and systems? And even is there one?
Well, we're trying to do that with this digital SI framework under the CIPM and BIPM. Whether we will succeed or not depends on building community consensus, and it's almost like it's a grassroots effort. We're doing our best, and the whole rationale behind this workshop is to engage you all as participants in moving this forward. So please help us. We will try to do this under the BIPM and CIPM, and we really need your engagement to help us move it forward.
I will make comment that I'm glad that the question said linking all codes and systems rather than trying to unify or harmonize all these systems.
Yeah. Thank you. So maybe I have a kind of a follow-up question on that. There are quite a number of different encoding scheme description of the units, and also particularly like Bob has mentioned that we have so many different domains and community of practices, and then they will exist because they have their own special language for their, you know, measurement units and so on. From the point of view of unit representation and also the work that metrology body does, is there something in the unit representation, any kind of extension that the metrology community can do or provide to enable, particularly in the case of Industry 4.0 kind of application, to make machine-to-machine data communication more reliable, quality of data more certain, so that we can trust and have confidence in the kind of data that we receive and we compute with machines and so on. Is there something that the metrology community can do in extending what is already available in the system now?
Oh, absolutely. I think the onus is on us to take leadership in this space. We trace back to the SI. We trace back to the fundamental units and fundamental constants. I mean, if nobody, who else is going to do this other than us in the metrology community? And we need to reach out and build bridges and build interoperability levels, layers to make this happen. I mean, this is on us. This is on us totally.
Yeah.
Steve, from your experience, what is your view?
I agree. I think this body is the right body. That's one reason I'm very happy I was able to attend. We ourselves in QEDT have thought about where should the QEDT ontologies go? Should they be embedded in a W3C standard or some other organization? But I think clearly the traditional SI bodies are, if you like, the high temple, of units. So that's the logical place. That's the logical organization to make the call and try and manage this for the world. We need to get our arms around this. Yeah. It's worked so far, well on paper in the paper world last century. And now we need to recognize that we have Internet of Things. We have all kinds of embedded systems. It's high time. I've been singing this, for, as Bob knows, for a number of decades, but since even when I was at NIST, but NIST wasn't, I think at that time, ready to hear some of these things. And for a good reason. I think the metrology community, I'm not a metrologist, so you can shoot me if you like, but the metrology community is very careful about changes, right? That's the way you have to be very that's right. And so I can see how, a relatively young technology, computers and not to mention machine learning or something, could be seen as a very nerve-wracking endeavor for the metrology community. So I think I would suggest the metrology community move carefully, but has to recognize they have to move reasonably quickly because technology is moving very quickly. So in order to remain relevant, I think it's important.
Okay, thank you very much for that enlightening remark. Unfortunately, we have run out of time, and I think there's still some more question in the chat box that we could not address, but rest assured the question will be collected and then addressed separately. So thank you very much, Steve and Bob, for being in the panel with us in this wonderful discussion. And I thank Victoria for posing the question from the chat and monitoring the question from the chat board. And last but not least, thank you very much, our backroom manager, Benjamin, for hosting us and sacrificing his sleep. Thank you. And thank you, all of you, wonderful audience in participating in these 2 days of event and sessions. Please remember that you have a session next tomorrow. There will be a parallel breakout session. It will run from UTC 5 a.m. So that's different time from this session, UTC 5 a.m. to 6:40 a.m. Tomorrow. So there'll be 4 topics in 4 different parallel breakout room that you can attend. Please do so tomorrow. Thank you. Thank you very much. And bye-bye.
Thank you.
Bye. Good night. Good night.
Thank you. Get some sleep.